Hello everyone, this is lecture 3 of ComSci 142, Search Algorithms. In this video, we will discuss 4 search algorithms, namely linear search, jump search, binary search, and hash-based search. When we talk about search, maybe the first thing that comes to mind is Google, because that's what we use to search for things on the internet. Or it could also be a game where you're searching for things, or searching for words, or looking for Waldo, right? But there are also other types of search, like maybe beauty pageants, right? That's also a search. Or you could just be looking for love, right? Searching for love. But what is the search problem more formally? So in the search problem, your input is a collection of items, and the output is the item that you want to find, or it could also be null if the item does not exist. Okay? So you're supposed to find the item with specified properties. Okay? So that is the search problem. Well, now, when we say collection of items, it's a general term. It could mean an array or an associative array, like a dictionary. So it doesn't matter if it's an array or a dictionary, as long as it's a collection of items, you can do search on it. Okay? And take note that the collection could contain duplicate values. So be careful about this, because you could be looking for like a specific item, or look for all items that match the criteria. Okay? Now, there are 3 fundamental search queries. We have existence, retrieval, and associative lookup. So existence asks the question, does the collection contain the target element? So does the target element exist in the collection, basically? Okay, so this will return true or false. Is it there or not? Next is retrieval. In retrieval, we return the element that matches the target element. So we're supposed to get it, retrieve it. Okay? So it could be a full or partial match. So it could match the description fully, or pwede man na partial match lang, and you could also return it. Okay? So it returns the item that matched your specifications, or it could also return null if it did not find the target element. Okay? And finally, we have associative lookup, which returns information in the collection associated with the target key element. So, in associative lookup, you have an associative array or a dictionary that has key value pairs. So, given a key, return the value associated with that key. Okay? Or, you could also return null if the key does not exist. Okay? So, those are the 3 fundamental search queries. Okay, so let's now go through 4 basic search algorithms, starting with the easiest one, which is linear search, also known as sequential search. So, linear search is the simplest searching algorithm, and it uses the brute force method. Okay, so you just have to sequentially go through each item in the collection. So, just check it one by one. That's why it's linear, right? So, is this item what you're looking for? No. Go to the next one. Is this it? No. Is this it? No. Is this it? No. And so on. Until you find it, or until you've reached the end of the collection. So, the pseudocode is fairly easy, right? You just have a for loop, right? For I from 1 to n, where n is the number of items in your array. Check if array at index I is the query item. If it is, then you return true. Otherwise, when you've searched the whole array and it's not returned yet, then you return false because it's not there. Okay. If you're not looking for existence but you want to retrieve the index of the item, then return the index I instead of true or false. Otherwise, return null if it does not exist. Okay, so fairly simple. Okay, so let's try it on this example. Let's look for 3 in this collection. So You start with 5, no. 9, no. 4, no. 3, yes. So we've found it here. Next, let's look for 5. So 5 is here right away in the first item. So we were lucky because it's in the first item and we can return it right away. Now, how about if we're looking for 8? So let's check. 5, no. 9, no. 4, no. 3, 6, 2, no. And then 8. So we've found it in the second to the last part of the item, of the collection. Okay. Now, how about if we look for 1? So we'll have to go through 5, 9, 4, 3, 6, 2, 8, 7 until we reach the end and we did not find 1. So we'll return false, it does not exist, or null if we want to return the index. Okay, so 1 does not exist. So we've reached all the way to the end of the collection and found out that, well, it's not there. Okay, so that's linear search. Fairly easy, right? Now, there are some variations to the linear search. So we'll discuss 3 variations to this. So the first is the move to front on success. And as the name suggests, once you find the item, so upon successful search, you move it to the front. Now, why would you do this? This is suitable if there is an increased chance that the query item will be searched again. So by searching it once, there's a more likely chance that you'll look for it again later on. Then you move it to front so that it's easier for you to find it on the next time that you will look for it. Okay, so let's say, for example, in this one, if you look for 7 and there's a likely chance that you look for 7 again, then it's better for you to move this all the way to the front so that it would be found easier later. Okay, so the move to front on success is used in most recently used paging algorithms. So you'll learn more about this probably in your junior year, in your 125 in operating systems. Okay, but yeah, that's the first variation, move to front on success. Now, the second one is move up on success. So it's similar to move to front, but you don't move it all the way to the front. You only move it 1 space forward. Okay, so you only move it up 1 time, not all the way to the front. Okay, so you use this when you don't want to move a lot of elements, because if you move it to the front, you'll have to adjust the rest of the items, right? But in move up on success, you're only swapping 2 elements, right? Okay, so if you don't want a lot of movement, use this one. Next is move to end on success. So this is the opposite of move to front. Okay, so if earlier you wanted it to move to the front because there's a higher chance that you're gonna look for it again, ang move to end on success naman is suitable if it's unlikely that the query item will be used again. So like if you look for it now, then probably you won't look for it later. So because it won't be used later, you can move it all the way to the back, because that would mean that other items could be like moved forward and they could be found faster. Does that make sense? Okay, so this will improve the performance of future searches as well. Okay, so those are the 3 variations for linear search. Okay, so what is the best case for linear search? So the best case is if the item is at the what part? If the item is at the front part or at the very first, right? Because then you won't have to do a lot of iterations because it's already found at the front. At the average case, the item could be somewhere in the middle, but it's not necessarily exactly in the middle, but in the middle area. Okay, that's the average case. And the worst case is if the item is at the back part or not in the collection at all, because then you would have to traverse the whole list to go to the back part, or to find out that you have reached the back part and it doesn't even exist. Okay, so that's the worst case. So for the running times, the best case running time is O of 1, constant time, because it's already at the front. Okay, so that will only take a constant number of steps. the average case is O of n because the middle part is okay. So the middle part would have to be somewhere around n over 2, right? But n over 2 is also O of n squared. Not n squared, but O of n, right? So it's still O of n. Okay? So your average case is still O of n. So like for example, if n is equal to 10, the half would be around 5, so maybe around 3 to 5 to 7, around this one. That's still O of n. Okay? And at the worst case, it's at all the way at the back, so O of n man ang worst case running time. But it doesn't consume extra memory, so the memory is O of 1. So no extra memory needed. Okay? So that's linear search. So another advantage of linear search is it doesn't put restrictions on the structure of the input, unlike the next two algorithms that we'll discuss. So it doesn't matter if it's ordered or sorted or not. Linear search will work just fine because anyway you're just going through it one by one, right? So it's useful for collections that may or may not be ordered or sorted, okay? Because it doesn't put restrictions on the structure of the input. So linear search is reasonably efficient for small and unordered collection of items, but when you go to bigger and a bigger data set, linear search might not be as effective, because then you'd have to search for, let's say, if you have 1 million data points, then you'll have to search up to 1 million iterations, right? So yeah, that's linear search. So an improvement to linear search is the next one, which is jump search. Okay, so it's similar to linear search, but we check fewer elements by jumping ahead. Okay, so we don't go through each item one by one, but we jump few steps ahead. Okay, and then the kicker here is that you have to assume that the array is sorted. Okay, so that is the caveat of doing jump search, is that you have to assume that the array is already sorted for you to be able to jump safely. Okay, so you have to pre-process the array or the collection by sorting it. Okay, and once you have sorted it, then you can do jump search. Okay, so how does jump search work? So it's similar to linear search, but you jump ahead by a fixed number of steps, and that allows you to skip some items entirely. But so you skip checking some elements, and when you've jumped too far, you will do a backwards linear search. Okay, so how does that work? Okay, so let's say that this is your collection from 1 to 9, and let's say that we're looking for the number 5. So you start at 1, and then let's say we jump by 3s. So by 3, it's 4. It's not yet 5. So we jump by 3s again, jump to 7. But 7 is already greater than 5. And because we know that this is sorted, we know that we have already overshot our jump, right? We have already exceeded if 5 does exist. So what we'll do is we'll do a linear search backward. So is this 5? No. Is this 5? Yes. So we have found 5 here. Okay, so that's jump search. Jump ahead and then check if it's still safe to jump forward, meaning the number currently is still smaller than what you're looking for, so jump ahead. But if not, if it's already greater than the number that you're looking for, then do a backwards linear search, okay, until you've either found it or you've reached the previous jumping point, and at which point you're sure that it's not there. Okay, and this is possible because the assumption is that the collection is sorted. Okay, okay, so oh, excuse me. Okay, so where were we? So this is the pseudocode for jump search. So given an array A and the query item, so we have to determine the how many items will jump over. So this is specified by the variable jump. Okay. So what we'll do is we'll take the square root of n being the number of items in the array, and take the floor if that's a like a it's a floating point. So we'll take the floor of that. So basically square root of n. Okay. So let's say, for example, here 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 items. So square root of 9 is 3. So we'll jump 3 items at a time. Okay. And we'll also duplicate the last element as the guard, just so hindi siya it doesn't overshoot, or like it doesn't fall off the edge without checking the last element, because there are some instances wherein, for example, from 17 and then you plus 3 this one, it's already off the end, but there's still 25 here. Okay, so we'll just duplicate the last element as a guard, and then we'll go through the array, but instead of incrementing it by 1, we'll increment it by jump number of steps here. Okay, and if the item at that index is already the query item, then we've found it. Otherwise, if it has already exceeded the query item, if it's already greater, then we'll do a backwards linear search from I minus 1 down to I minus jump. So your stopping point is the previous jump point, for example. Okay, so that's it for jump search. So in this example, we have 9 items, so the jump will jump by 3. So let's say that we're looking for 17. So we'll start at 1, jump by 3 steps, 9, so it's not 17 yet. Jump by 3 steps, 17, and we have found it here. Next, let's look for 28. So 1, jump by 3, 9, jump by 3, 17, jump by 3. There should be a 25 here. So we've already reached the end of the array, and it's not there, so 28 is not found. Okay, next, 11. 1, jump by 3, 9, jump by 3, 17, but we have already exceeded 11, so we'll do a backwards linear search. That's 15 and then 11. So we found 11 here. Now how about if we're looking for 10? So we'll do the same thing. 1, jump by 3, 9, jump by 3, 17, then go backwards because we've already reached or exceeded the query item. So is this 10? No. Is this 10? No. And then we've reached the previous jumping point, which was 9. And at this point, we are sure that 10 does not exist because this is already sorted and we've reached the previous jump point. Okay, so that's jump search. Okay, now how did we get this square root of n as the value for our jump? Okay, so let's try to analyze this one. How many iterations does the jump search have, or what is the running time basically? So for the running time, there could have been n iterations if it was linear search, right? If the n is the number of items in the array. Okay, it would have been n if it was linear search, but since we are jumping jump at a time, so let's call j as our jump. If we are jumping j items at a time, then this would be reduced to n over j, right? So for example, here, if n was equal to 9 and our jump was equal to 3, then there would be a total of how many iterations? Only 9 over 3, which is 3 jumps, because starting from 1, so you jump 2, you jump 3, that's it. And then when you jump, you've already fallen off the end of the list, right? So that is the number of jumps, n over j. However, you also do the backwards linear search, and at the worst, you will be doing j minus 1 iterations of this one, because for example, if we're looking for 10, so from here you'll only look for it up to here, so that would be 1, 2 iterations only, and then when you check here, it's already the boundary. So that's j minus 1, which was 2 for the backwards linear search. Okay, so this is the running time, n over j. This is for the jumps, and j minus 1 is for the backwards linear search that you'll have. Okay, so what should be the optimal value for j? Now, if j is too big, like if you make big jumps, like instead of 3, maybe we did, let's say 5. Okay, what would be the implication? If you jump too big, then from here to here, then from here to here, then you would have a small number of jumps, which is good, but then your backwards linear search would also be bigger, right? Because then you'd have to traverse more items backwards. Okay, so it won't be optimal if it's too big. Now, what if j is also small? So if j is small, the backwards linear search will also be small, because then you'd have to, let's say kung by 2s lang, then the backwards linear search would only be 1, right? But then you would have more jumps. Okay, so you'd have to balance it being big or small. Okay, and the reason why we used square root of n is because that is actually the optimal number for the jump. Okay, so let's clear all of this and check why it is the optimal jump. So we said that the running time was n over j plus j minus 1, right? This is the running time. Now, remember from your calculus class that if you want to get the optimal value for a for the equation, just get the derivative and equate it to 0, right? So since we want to find the optimal value for j, then we'll get the derivative of this with respect to j. Okay, so get the derivative of this with respect to j. So this is n times, so over j is j minus 1, right, plus j minus 1. So j raised to negative 1 is just over j, right? So if you get the derivative of this, that would be, so negative 1 will be here, n tapos j, this will become minus 2. Okay, and then this one will become 1, and then this one will be removed. Okay, so that would be negative n over j squared plus 1, and since we're looking for the optimal, we'll equate it to 0. Okay, if we transfer the plus 1 here, that would become is equal to negative 1, and if we multiply everything by negative 1, then it becomes n over j squared is equal to 1. Now if we transfer j squared to the other side, this becomes n is equal to j squared, right? And so the optimal value of j is equal to square root of n. If we take the square root for both sides, so if we take the square root of this would be square root of n, this one would be just j. So that is the optimal value for j, is square root of n. Okay, because that will balance the number of jumps with the backwards linear search that you'd have to do. Okay, so that is why the optimal jump is square root of n. Okay, So that's it. And so if you have jump search wherein you have n items and the jump is square root of n, and you have square root of n as iterations, the best case is O of 1, because the best case is if it's already at the front also. Average case is square root of n, because that's the half of the jumps. It's still square root of n over 2 is still square root of O square root of n. And the worst case again is if you have to do all of the jumps, which is also O of square root of n. But this also does not take any extra memory, so it's still O of 1, constant memory. Okay, so that's jump search. Next, let's look at binary search, which uses the divide and conquer technique. Okay, so we'll learn more about divide and conquer in later lectures, but basically binary search will use this paradigm, and it also assumes that the array is sorted. Okay, so just like your jump search, and if the array is not yet sorted, so you'll have to do a pre-processing step that you will have to sort the array. Okay, so you're probably familiar with binary search already, but just to review, basically what you'll do is you'll divide the sorted collection in half. Okay, and you'll first look at the middle, and then if that's already the item that you're looking for, then good, you've found it. If not, you look for the item in the correct half based on the middle. If the item is bigger than the middle, then you look for it in the right part. If it's smaller than the middle, look for it in the left half. Okay, so you repeat this process until you've found the item, or you are sure that it's not in the collection. Okay, so this is the pseudocode for binary search. So you start at the starting point is 1, the end point is n, and while start is still less than or equal to end, then you look for the middle part, which is start plus end over 2. If the query item is already the mid index, then you return that you found it. Otherwise, if you have if the query item is less than the middle, then you move the search to the left half by replacing the end with mid minus 1. Otherwise, you move the search to the right half by making the starting point be mid plus 1. Okay, so let's see some examples. So let's say in here we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 items. N is equal to 8. So the start is at 1. The end is at 8. So the middle right now is 1 plus 8, which is 9 over 2. This is 4.5, but let's just round this up. Let's take the ceiling. This would be index 5. So 1, 2, 3, 4, 5. So this would be our middle. Okay, at index 11. So let's say that we're looking for 8. Okay, so the middle is at 11. Is it 8? No. 8 is less than 11, so we'll move the search to the left half. Okay, so we'll move it here. So what we'll do is we'll adjust the end to be this one. So now, basically, we're looking for 8 only at this part from start to end. Okay, so the half here is 1 plus 4, that's 5 over 2, 2.5. Take the ceiling, it's 3. So at index 3, you have found 8 already. Okay, now let's look for one more. How about if it's 17? Okay, if it's 17, we do the same thing. So we start at 11, but this time 17 is bigger than 11, the middle. So what we'll do is we will move our search to the right half by making this the starting point and not this one anymore. Okay, and then the middle is already 17, so we have found it. Okay, so you do this repeatedly until it's found or sure ka na it's not in the array. Okay, and then lastly, let's look for 10. We can just eyeball it and see that it's not there, but what would the binary search do? Okay, so same thing. So 11, it's not there, so we'll move to this half. 8 is also not there, so but 8 is smaller than 10, so we'll have to move it to this end. So we'll start here, and then 9, it's not there, and since we cannot find anything anymore, because then the start and end would overlap, we can stop the search and say that there is no 10 in this collection. Okay, so that's binary search. Basically, if this is your collection, start with the middle. If it's greater than the middle, then move your search to the right half. If it's less than, then move it. No, that's the wrong one. Oh yeah, if the middle is less than the item, and then if the middle is greater than the item, then you move it here. Okay, so that's binary search. For the best case running time, it's O of 1, because the best case is if it's already in the middle, so you'll only need one step. Average case is log of n base 2. And why is this? So remember that log of n base 2 is, for example, if you have 8, if n is 8, log of n base 2 is equal to 3, right? Because 2, oh no, sorry, not 3. This is wrong. Tama ba? 3 nga. Log of n base 2 is 3. Because 2 cube is 8. Right? So, why is it 3? Because basically the most that you can divide 8 in halves is 3 times. So, like 1, 2, 3, 4, 5, 6, 7, 8. So if this is the middle part, so that's 1. And then if you look for it here, and then this is the middle part, that's 2. And then if it's here, and then this is the middle part, that's 3. But you cannot divide it further than that. Okay, so that's the average case. And the worst case is also log of n base 2, because the worst part is if you've already done everything, but then it's not found, right? So yep. And you also don't take any extra memory because you're not saving anything anyway, right? So O of 1 memory. Okay, so that's binary search. And binary search is useful when the collection is already pre-sorted. Okay, so you add a small amount of complexity, which is sorting, for large performance gains, which is log of n. Because earlier, you'll notice that, so let's try to compare what we've had so far. For linear search, it was O of n, right? For jump search, it was O of square root of n. And then for binary search, it's O of log of n. So we've constantly been improving as we went. We've constantly been improving from O of n to square root of n to log of n. So this one is the best one so far. Okay, so now if you're trying to do search and insert, like if you look for it and it's not there, then you insert the item. So if it's not found, insert it. the final value of mid is where the missing item should be inserted. So where you stop your search in binary search is also where you need to insert that item, that missing item. Okay, and then you need to adjust other items by shifting it forward. Okay, however, what if your data or your collection is dynamic? What if the collection is constantly updated? If you're doing a naive insert of items, then you'd have to extend the array and push around half of the elements forward to accommodate that insertion. Or if you're deleting, then you'll have to move around half of the elements also backward, and you'll have to shrink the array. So this one is actually not that efficient. So it has unacceptable performance, especially if you are doing frequent insert and delete operations. Okay, so the solution is to use hash-based search. Okay, for this one, if you have dynamic data. Okay, so for hash-based search, we will have to use a hash table. Okay, so what is a hash table? So a hash table comprises of a lookup table and a hash function. So a lookup table is basically just an array. Okay, and the meat of the hash table is really the hash function. So the hash function will map your query item to an index value for the hash table. So what does that mean? So a hash function could look like this. So h of x is equal to x modulo n. So remainder of the x when it's divided by n. Okay, so let's see an example. Given these input items, what would their values be if we use this hash function? Okay, so let's see. So what are the possible values for x modulo 3? So if it's modulo 3, that would have to be remainder of a number divided by 3 could be 0, 1, or 2. It can't be 3 because if you have a remainder of 3, then that's already fairly divisible, evenly divisible. So your results can only be 0, 1, or 2. Okay? If it's 1 modulo 3 is in 1. 4 modulo 3 is also 1. So 4 will be placed here. How about 8? 8 modulo 3 is 2. So we'll put it in 2. Ang 9 modulo 3 is 0 because you don't have any remainder. 11 modulo 3 is also 2. 15 modulo 3 is also 0. 17 modulo 3 is 2. 21 modulo 3 is 0 because it's evenly divisible. Then 25 modulo 3 is 1 because there's an extra from 24. Okay, so this is basically the purpose of a hash function, is that instead of like just an individual index like 0, 1, 2, 3, 4, 5, 6, 7, 8, you can put them in indices according to the hash function. Okay, and you will notice that we have fairly distributed all 9 items into 3 buckets of indices. Okay, so na fairly distributed sila. Okay, so what we'll do is we'll load the collection of items into the hash table by using the hash function, and whatever the value of the hash function is, that would be our index for the hash table, just like what we did. Okay, so shouldn't have erased that one. Okay, so maybe I'll rewrite it. 0, 1, 2, 2 set 9, 15, 21, 1, 4, 25, 8, 11, 17. Okay, so when we have the collection, we will create the new array. So this is the hash table itself, and then for each item in the collection, we will get the hash function, hash value of the item, and then that would be our index, and this would just be a linked list. Okay, so we'll add the item to this linked list indexed by the hash value. Okay, so if we are looking for the item, then for example, if you're looking for search for number 4, what will we do? So we'll take the hash of 4, which is 4 modulo 3, that is equal to 1. So we know that we have to look for 4 in index 1. Okay, because if we placed it in the table, then it's in index 1 because we follow the same hash function. And indeed, 4 is found here. Okay, and what we'll do is we'll just linear search through the linked list, assuming that it has few items because we have fairly distributed them across all the buckets. Okay, so putting all of that together, this is the hash search. So get the hash of the query item. So the list that you'll be looking for is indexed by the hash value h. If the list is empty, obviously it's not found because there's nothing there. And otherwise, you go through a linear search using the list and the query item, and then return true or false depending on the result. Okay, so the performance of hash-based search depends on the quality of the hash function, because if you have a bad hash function, then it will not evenly distribute the items. Okay, but in general, this has better average case performance than the previous search algorithms that we've discussed. Okay, and we usually use hash-based search on large collections, just so we can narrow down where to look for, because we're using hashing. Okay, so for the running time, best case is O of 1 if you can, like, if the list is empty, or if the list is easily found in the, like, maybe it's the first item on the linked list, so that's good. Average case is also O of 1 because it usually takes constant time to traverse a linked list in the index, especially if it's fairly small. But the worst case is O of n, and again, this is dependent on the quality of the hash function, because maybe you can have something like this, like 0, 1, 2. If it's h of x is equal to x modulo 3, let's say, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8. So that's fairly distributed. But what if your h of x is equal to x plus 1? So what will happen? So let's say if you have 0 to 5, it would be 0, 1, 2, 3, 4, 5. And let's say we have 1, 2, 3, 4. So 1 will be placed in 2, 2 will be placed in 3, 3 will be placed in 4, 4 will be placed in 5. But then there are few items in each list, but you'll have to imagine that this list will only contain one item because you're only it's exclusive to x plus 1. So although the linked list is small, you'll have to imagine that the hash table will be fairly big. So it's similar to just linear search still. So this is also a bad function. Another bad function is something that maps it to just maybe like one maybe x divided by 2, or x okay, let's try another one. X divided, or x percent 2. Okay, so if you have x percent 2, then you are sorting between odd and even numbers. So basically you have 0 and 1, and if it's from 1 to 100, then you'll have 0, 2, 4, 6 all the way to 100, and then you'll have the odd numbers here, 1, 3, 5, 7, 9, and so on. So there will be a big number here as well. Okay, so and although this is the case, this is actually fairly good because more or less you have divided it into two. The bad hash functions look like this. So maybe like 0, 1, 2, 3. Maybe isa lang de, like A, B, and then everything is here, like C, D, E, F, G, H, and so on. So if you're lumping everything together in one bucket, then that's bad hash function. Okay, and you'll get the worst case running time of O of n because it's close to like doing a linear search on everything anyway. Okay, so and unlike the previous search algorithms that had constant memory, this one will have O of n memory because you'll have to store all of the items into the hash table. So that's O of n. Okay, so the goal of a hash function is to distribute items equally across slots. So the bad hash function design leads to poor distribution of keys, as I mentioned earlier. So a poorly designed hash function has many unused slots, which is a waste of space, and it also has many collisions, just like what we showed earlier, wherein a lot of items are mapped onto the same index. So it worsens performance because then you'll have to take a longer linear search. Okay, so collision is what happens when two keys are mapped to the same slot in the hash table. Now, collision is inevitable because if you don't have collisions, then that means that you're just doing a one-to-one mapping of everything, which just means that you're doing basically still like not a linear search, but you're not really doing any performance gains because anyway it's you're storing everything in memory. Okay, it would be a bigger hash table. So what happens when two keys map to the same slot in the hash table? So this is possible, right? Just like what we saw earlier, we can have 0, 1, and 2. So 3 and 6 could map to the same hash number. Occurs when the number of slots is less than the number of possible hash function keys. So there would be collisions inevitably. And there are two main ways to handle collisions. So one is the separate chaining, which is what we did by creating linked lists. So 0, 1, and 2. So if you have 3 and 6 using X%, so move that one, X%3, so they'll both be mapped to 0, right? So this is separate chaining. You're using a linked list for all items that are colliding. But another way to do this is by using open addressing, by doing linear probing. So you can read more about this later, but the basic idea is okay, something like this. So you won't create like a hash table, but you'll just use a normal array like this. Now let's use the same example, X%3 for the hash, and then 3 and 6. So what will happen is X%3 for 3, that would be 0, right? So it would be placed in index 0. But now when we do 6, so 6 is at, or maybe we'll do 5 first. 5. If it's 5, what we'll do is 5%3 is 2. So it will be placed in index 2. So far, okay pa, because there are no collisions yet. Okay, what if we put 6 this time? 6%3 is also 0. But if we put 6 here, there will be a collision because 3 is already in index 0. So what we'll do is we'll look for the next open address which is at index 1. So the next one is here, and we'll put 6 there. Okay? Now what happens if you have something like 4? 4 modulo 3 would be 1, right? So it's supposed to be at index 1, but it's not open. So we'll look for the next one. So is it possible here? No. So you'll insert it in the next open slot, which is here at 4. Okay, so that is open addressing. Now when you are looking for it naman, when you're retrieving, like let's say is 4 there, you'll do the same process, but you start at index 1, but you don't stop right away if it's not equal, because it could have been displaced somewhere else, right? So is this one 4? No. So you go to the next. Is this one 4? No. Is this one 4? Yes. So you have now found it. Okay, but how about if we look for, let's say, 7? So 7 modulo 3 is also index 1. So we'll start looking for 7 at index 1. 7? No. 7? No. 7? No. And then when we reach an empty slot, that means that we can stop looking for 7, because if 7 has been inserted, then it would have been inserted here. Okay, but since we've reached an open slot, then we are sure that 7 is not found. Okay, so that's the basic idea for open addressing using linear probing. Okay, so there are 2 ways to handle collisions in hash tables. Okay, so that's it. And to review, we discussed 4 search algorithms. So linear search is just going through each item sequentially, one by one. It usually runs in O of n, right? So this one is O of n. And then we discussed jump search, which needs the array to be sorted, and we can jump square root of n items at a time and do a backwards linear search if we have overshot our jump. So the running time of this is O of square root of n. And then for binary search, this also assumes that the array is sorted, and then we'll look through the middle, and then depending on whether the query item is less than or greater than the middle, we'll move the search to either the left half or the right half, and then do it repeatedly until we have found the item or sure na it's not in the collection. Okay, and it runs in O of log n. And then finally, hash based search, whose running time depends on the hash function, the quality of the hash function. So basically you'll use the hash function to get an index, and you put your item in that index. Maybe here we have the 7 and 9, and in here we have 11 and 13. So something like this. So the goal is to distribute the items into buckets in the hash table, and do it in a way that it's fairly distributed, so that you can just do a linear search fairly quickly on each index. Okay, so that's it for search algorithms. We'll stop here. Of course, this is not the only search algorithms out there. So there's a lot more other related algorithms for search. Okay, but the important thing is that if sorting and searching are somewhat related to each other, because preliminary sorting can help search faster. Okay, so however, the downside is that it's costly to maintain a sorted collection of items, especially if there's frequent insertion and deletion. So you'll have to balance the trade-off of that one. Okay, and then in next meeting or next week, we will be looking through several sorting algorithms that will help us do this. Okay, so that's it for this video, and I will see you next time.